We can begin. So, thank you very much for coming. It's always a pleasure to have you. And it's a pleasure to have Professor Ratul Lahkar from IIM Udaipur. So, who will be talking about large population aggregative potential games. So, he has published heavily in Journal of Economic Theory and other prestigious journals, including Games and Economic Behavior and so on. So, I'm sure the talk would be of considerable interest to a number of you. So, you have 1 hour and some questions and answers.
Sure. Okay. So thanks for inviting me and coming for the talk. So I'm going to talk about the general class of games which are called potential games. So they are well known in game theory, and the concept was first given by Monderer and Shapley, and it was extended to what we call large population games. I'll just discuss what those large population games are by Sandom, who is actually my advisor. So the reason why potential games are of interest is, at least to me, is that they have attractive evolutionary properties. So that's why they can be widely used in evolutionary game theory, in which we can then show that, at least for these games, we have convergence to Nash equilibrium under a wide variety of evolutionary dynamics. The reason why that is important is that the question of how people actually coordinate on a Nash equilibrium is not very clearly resolved in classical game theory. We just characterize the equilibrium and leave it at that, without really specifying how people actually manage to find a Nash equilibrium. But under evolutionary game theory, we can actually make that question more precise and talk about how people actually may converge to Nash equilibrium, even if to begin with they were not playing the Nash equilibrium. Okay? And it turns out that in potential games there is convergence to Nash equilibrium under a wide range of evolutionary dynamics, which makes the prediction of Nash equilibrium in these particular games particularly robust. Now within potential games, I am going to talk about one particular class which are called aggregative potential games. So aggregative potential games combine two concepts, aggregative and potential. So aggregative games are games in which the payoff of a player depends only on that player's own strategy, which is of course natural, and also on the aggregate strategy level in the population. Okay? It does not really matter which among his other rivals are doing what. What matters is the aggregate strategy that his rivals are playing. For example, the simplest model one can think of is a Cournot competition. In a Cournot competition, if I am the producer, I don't really care about the output choice of each of my individual rivals. What I really care about is what is the sum of the output that my rivals are producing. Okay? So that is an aggregative game. And aggregative potential games are potential games which are aggregative. Okay? Now as we will see, these games are, well, I am calling them simple because they can be analyzed using a one-dimensional analog of the potential function. So by the way, the formal definition of a potential game is that they can be summarized using a real valued function which is called potential function. Okay? Now a potential function can be quite a complicated object, but in aggregative simple games this potential function can be further reduced to a one-dimensional function which we call the quasi potential function, and I am going to focus on one particular application, which is the tragedy of the commons. So why should we care about the tragedy of the commons in this particular framework? Well, the reason is, I mean, apart from the application I am going to talk about later on, this is interesting because an evolutionary analysis of the problem adds some new perspective. So tragedy of the commons is of course a well-known model in microeconomics, and it is known that it manifests when large number of anonymous agents interact. Anonymous agents means that people should not know each other very well. The reason of course is that if people are not anonymous, they can use repeated game strategies to punish deviations from the social optimum, in which case the tragedy can be avoided. But if people don't know each other very well and the number of people involved are large, then it becomes difficult to use repeated game strategies, and in that context evolutionary game theory becomes useful, because it is used precisely when we have the interaction of a large number of anonymous agents. Okay? So, if we now model the tragedy of the commons as a potential game, then we can show that there will be convergence to Nash equilibrium, and as we all know, and this of course we do so formally, but from standard microeconomics we know that in the tragedy of the commons, the Nash equilibrium is inefficient. Okay? So, we will have the convergence to the inefficient Nash equilibrium under a wide variety of evolutionary dynamics. So, one way to appreciate this result is that it explains the ubiquity of the problem. Why tragedy of the commons is so common. Okay? I mean, it manifests itself in a variety of contexts. Anyway, so okay, so we'll talk about the tragedy of the commons later on. First, let us set up the model. So this is a description of the general model of population games. So population games, you can think of it as a society consisting of a continuous population of agents. So the population games are basically what are called non-atomic games. So what are these non-atomic games? It means that each individual agent is so small, technically they are of measure 0, which means that each individual agent doesn't have any impact on aggregate variables. Okay? So the model of perfect competition is a non-atomic situation, because in the purest form of perfect competition, each firm is of measure 0. It doesn't have any impact on the market. Okay? So this is the formalization of that notion, and we assume that the mass of the population is 1. Okay? So each agent in the population has a strategy set which we call S, and let's assume that there are n strategies. So we think of the set of social states, okay, which is basically the set of probability distributions over this set S. Okay. What is the interpretation of this? The interpretation of this is that, so the scalar xi, which belongs to this vector x, is the proportion of agents who use strategy I. Okay. Then there is the payoff function from the set of social states to Rn. I mean, there is a technical condition about Lipschitz continuity and all that. So Fix is the payoff to strategy I when the social state is x. So in population games, the payoff of an agent depends upon his own strategy and the social state. Now the social state, remember, tells us the distribution of strategies in the population, which strategy is being used by what proportion of the people. Okay? Individual identities are not important here. I mean, what is important is the proportions. Okay? And then we can define a Nash equilibrium in the standard way. It will be a social state x such that if strategy I is in the support of x, that means that if it is being used by a positive mass of people, then at that x, strategy I should be a payoff maximizer. Okay? So that's the standard definition of a Nash equilibrium. An evolutionary dynamic operates in x and tracks changes in x as agents revise strategies. So the way, roughly speaking, evolutionary dynamics work is that, so we have so let's suppose that there are 3 strategies. We can then show the set of social states in this simplex. Okay? So this is strategy 1, strategy 2, strategy 3. Let's suppose that this is the Nash equilibrium. Okay? Now in classical game theory, we will just characterize the Nash equilibrium and be done with it. Okay? But in evolutionary game theory, what we do is we allow the society to begin anywhere in this set. Let's say it begins here. That means so much proportion is playing strategy 1, so much 2, so much 3. Okay? And this can be, the initial state can be different from the Nash equilibrium. Okay? Then we introduce evolutionary dynamics. Okay? That tells us, so let's call it x0, the initial state. Okay? So an evolutionary dynamic, which can be of different forms depending upon what we assume about how people are behaving, will track how this x changes over time. Okay? It may or may not, so it may converge to the Nash equilibrium, or it may not converge also. That is also possible under certain games. Okay? The point about potential games is that no matter where you start, it will always converge to Nash equilibrium. Okay? So that's the broad idea. Okay. So now, so we are actually interested not in a full general format of population games, but in aggregative population games. Okay? So the definition of aggregative population game I use is something like this: that a strategy set S has this particular form. So basically, So again, there are lots of technical problems involved in doing evolutionary game theory on a continuous set. So instead of using a continuous strategy set, we use the discrete approximation of that set, okay, or finite approximation of that set. We then define Ax using this formula. So this is basically the aggregate strategy level in the population. Now in this particular model, because we are assuming that the mass of the population is 1, the aggregate strategy is the same as the average strategy. Okay. So think of this. So in a Cournot model, this would be the total quantity being produced. So this would be the all the possible quantities of output that the firms can produce. Ax will be the total quantity. Okay. In the tragedy of the commons, I mean the tragedy of the commons, the most basic story is that there is a common field in which villagers graze their cows. So S, this will be the number of cows that from 0 to m, number of cows that the villagers can graze, and Ax will be the total number of cows that are being grazed. Okay. So we call beta to be the aggregate benefit function and C to be the cost function. So so then we define the population game. So a population game is defined by the payoff function. Okay. So in an aggregative population game, the payoff function, or at least in aggregative population game that I am considering, the payoff function will take this particular form. The payoff from strategy I, when the state is x, okay, is given by I times beta Ax minus Ci. Okay. So in a Cournot model, beta will be the inverse demand function, right? So beta Ax will be the inverse demand function as a function of total output in the economy or in the market. So this will be the market price. So I will be the quantity being produced. So this is the total revenue minus the cost. Okay. So that would be an example of an aggregative population game. So we call games that have this payoff structure to be an aggregative population game, and we assume that beta and C are smooth and continuous and all that. Okay, so now let's define potential game. So potential game, well, there's a separate definition for classical, in the context of classical game theory given by Monderer and Shapley. But if you extend that definition to population games, then it takes this particular form, that a population game F is a potential game if there exists a function small f such that the gradient of small f is equal to f. Okay. That is, so remember that this x is x1 to xn, it's an n dimensional vector. Okay. So the gradient of f is basically the partial derivatives of f with respect to all the xi's. Okay. And fx is just the payoff vector f1, f2 up to fn. So a game is a potential game if this gradient is equal to the payoff vector, that is del f del xi is equal to fi. Okay. Now that will not always be true for any game, all games, but if it is true, then we say that that game is a potential game. So a simple example is, suppose f1 is 3x1, f2 is 2x2, f3 is x3. Okay. So that is there is a game with 3 strategies, and these are the payoff functions of those 3 strategies. So this is like almost like players are being randomly matched to play this pure coordination game. So think of these as the payoffs of the row player. Okay. The row player is randomly matched with a column player. Now the column player can be, so if the population state is x, then the column player can be someone who plays strategy 1 with probability x1, because x1 is the proportion of people who are playing strategy 1, and since the population is large, there is no difference between the probability and the proportion. Okay. Similarly, x2 is the probability that the column player will be playing strategy 2, and so on. So if the row player therefore plays strategy 1, then his payoff is 3x1 times 0x2 plus 0x3, which is 3x1, and so on. Okay. So it turns out that this is a potential game, and the potential function is this particular takes this particular form. That is, I mean, the way to check that would be that if you take the partial derivatives of this function with respect to x1, x2, and x3, you will get these values. Okay. Okay. So now, now it turns out that the potential games, I mean, apart from the technical definition, the mathematical definition, it turns out that they also have a nice economic interpretation. If I guess now, in any population game, we can think of this partial derivative, that is del of fi with respect to xj. I and j are two different strategies, measures the externality imposed by strategy j users on the payoff of strategy I users. So roughly speaking, what this is telling us is that if you increase the proportion of people who are playing j, how does the payoff of strategy I change? If this is positive, that would mean that there are positive externalities. That means if the proportion of j players increase, the payoff of I increases. If this is negative, then there are negative externalities, right? Now it turns out that in a potential game, now del fi del xj, by definition of the potential function, fi is del f del xi. So we can write this as this, okay? But then by Young's formula, this is just equal to this, where we are interchanging xi and xj, okay? And then this becomes this particular thing. So that is del fi del xj is equal to del fj del xi. That means in a potential game, these externalities are symmetric. That is, the externality imposed by j users on payoff of I is the same as the externality imposed on I on the payoff of j. Okay? And this is happening because this is true. I mean, this game is for a potential. Okay? Anyway, no, this is the property of the potential game which we are getting because of the definition. The definition comes from the fact that fi is equal to del f del xi. If this is not true, then of course this will not hold. So this will not hold if the game is not potential. The definition is this. Okay. So now, now recall that we are interested in aggregative games, and the aggregative game we are talking about takes this particular form. Okay. Now it turns out that this is a potential game, and the potential function takes this particular form. Okay. Again, I mean, this will have interpretation depending upon the context, but the simplest way to see that is that if you take the derivative of this with respect to xi, you will get this particular object. Okay. That is, this ax will come here, and remember this, that this ax is summation of ixi, and so this I will come when you differentiate this ax. Okay. So anyway, so a population game of this form, which is aggregative, turns out that it is a potential game, and hence we call games of this form to be an aggregative potential game. So let's look at the tragedy of the commons now in more detail. So in the tragedy of the commons, what do we have? We have we think of this I, which belongs to the strategy set S, as an input level agents use in a common pool resource. So common pool resource would be a resource which anyone can use, like a grazing field. So I will be the number of cows that people can graze. So ax will be the total amount of inputs people are using on this common pool resource. We think of pi ax as the output that is being produced when the total number of input is total amount of input is ax. So for example, if I denotes cows, ax is the total number of cows, pi x is the total number of output coming from total amount of output coming from this number of cows. Okay. We think of we take pi to the standard increasing and strictly concave production function. We then define the average product, standard definition, pi a divided by a, and because the resource is commonly used, this is the standard payoff function for a tragedy of the commons. It is amount of output, amount of input used by used by an agent multiplied by the average product, okay, minus the cost of that input. This is the standard payoff function used in the potential.
With the space of strategies, I mean, like X is like temporarily static.
Yeah, right now think of X as being static. We are not talking. We have not introduced evolutionary dynamics right now. Okay? So think of X as the as static. Yeah, I mean to characterize. So the first objective is to characterize Nash equilibrium. For all that, we don't need the evolutionary dynamics. We will talk about it later on when we want to talk about the dynamic issues. So right now, think of X as just given to us. Okay. So recall now that the general form of the aggregative potential game was this particular form. So here, therefore, this beta is just the average product. Okay. Hence, the average product is the aggregate benefit function, and from the general form of the potential function, we obtain therefore that the potential function here is it is integral of this with respect to the average product minus the total cost. Okay. Let's look at the issue of externalities with respect to aggregative potential games. So since the aggregative potential game has this particular form, recall the definition of the externalities is just del fi del xj, which in this case turns out to be this particular thing. Okay. So therefore, now since I and j are all positive by assumption, externalities just depend upon b prime, the derivative of beta prime. If beta is negatively sloped, then we have negative externalities. If beta is positively sloped, then we have positive externalities. Now of course, in the tragedy of the commons, well, before the tragedy of the commons, let's think of the Cournot competition. Recall in Cournot competition, beta is the inverse demand function, which in most cases will be a negatively sloped function. So in a Cournot case, we will have negative externalities, which basically means that if some producer increases output, then that will lead to a fall in profit of other producers. In the tragedy of the commons, we have assumed that pi is strictly concave, pi being the production function, which of course means that, I mean, again, this is standard that if the production function is concave, then the average product is declining. Okay, average product is strictly decreasing, hence externalities are negative. And again, but we already know that from standard microeconomic theory, elementary microeconomics, but this is just another way of looking at the same issue. Okay. So now we want to analyze these sort of games. Now, if you have a general potential game without any further structure, then there are ways to characterize the Nash equilibrium. There are results about that in the paper by Sandholm. But we are not going to use the general results. We are going to use the further trick to simplify the problem because of the special structure of our problem. So what we do is we introduce what we call the quasi potential function. Okay? So recall our earlier definition of quasi potential function. It's a one-dimensional analog of the potential function. So now the potential function, remember, sorry, where did it go? Yeah, the potential function is a function from the state space to R, the real values function. Now the state space, of course, has n dimensions, okay, depending upon the number of strategies. Okay, but the quasi potential function is just a function from 0M, which is the which is the continuous version of the strategy space. The strategy space in our example or in our model is this, okay, which is an approximation of 0M. Okay, so what we're now, when the strategy space is this, okay, then the aggregate value AX will take some value between 0 and M. I mean, the aggregate value will just be a convex combination of these numbers, okay, and hence the aggregate value will be any number between 0 and M. So basically what we are doing is we are taking the quasi potential function to be a function from 0M, which is the set of possible values of the aggregate value or aggregate input or aggregate strategy level. So we take this and it's a real valued function, and we define it in this way. The definition is very similar, except that if you this, so this is integral of 0 to Ax beta z dz minus summation of Cixi. This is the original potential function. Here this first part is very similar. Here instead of summation of Cixi, we just have C alpha. Okay. So we call it a quasi potential function, and there are a lot of relationships. All the details are in the paper, but one particular relationship you can immediately think of is that, think of what we call a monomorphic social state. Now, what is a monomorphic social state? Monomorphic social states are these vertices. That means at these vertices, these are 3 states in which the entire population is just playing one strategy. So that means here, if this is S1, that means everybody is just playing strategy 1. So that is x1 equal to 1, x2 equal to 0, x3 equal to 0. Okay. Similarly, here everybody is playing 2, here everybody is playing 3. Anyway, so monomorphic state is one of those vertices, and we denote it by the notation EI. EI is basically the basis vector, where for the ith value is 1 and everything else is 0. That means everybody is playing strategy I. Okay. So now, if everybody is playing strategy I, then of course the aggregate value will be I, okay, because the aggregate value is summation of I xi, right. So if all the xi's are 0 except for one particular value, then the aggregate value will be just that I. Okay. So then in that case, you can check that f e alpha, that is, if you take the state to be e alpha, then and you put this into the potential function, then it turns out that this is equal to g alpha. Okay. And the reason is obvious, that if it is e alpha, then the aggregate value is just alpha. Okay. So this ax just turns out to be alpha. So this part is the same. Okay. In this part, we have summation of ci xi, but all the other xi's are 0. So it is just c alpha. Okay. And so you get f e alpha equal to g alpha, and so g is a, well, we call it the limited one dimensional analog, but there are other relationships also which I am not going into all the details. Anyway, so now what we are going to do is we are going to use the quasi potential function to characterize the Nash equilibrium of these games. So what we are going to do is, in this talk I am just going to talk about the case where externalities are negative. Again, the paper has also considers the case of positive externalities, but that is more messy and you need to consider a variety of cases. For negative externalities, the results are much more elegant. So we assume that beta prime is strictly negative, and we also assume that C is strictly convex. You can also talk about C being linear, but again I am not going to talk about that here. Okay. Anyway, so under these assumptions, you can show that, so let f be an aggregative potential game with potential function small f, and let g be the quasi potential function. Then you can show that this f, the potential function, is concave on the state space, but not strictly concave, and g is strictly concave on 0m, that is the domain of g, 0m, with a unique maximizer which is some alpha star. Okay. So these are some properties that you can derive, which will be useful for us later on. The important thing here is that under these assumptions, the potential function is concave and g is strictly concave. Okay. Now there is a general result about potential games in the paper by Sandholm, that is, if the potential function is concave, then the set of maximizers of the potential function is the set of Nash equilibria of the game. That is, suppose you want to characterize the set of Nash equilibrium of a general population game. Now in general that is difficult, okay, but if you have a potential function or a potential game, then it turns out that it is much simplified. Okay. Particularly if the potential function is concave. If the potential function is concave, it turns out that you just need to maximize the potential function on the state space X, and the set of maximizers of the potential function will be the set of Nash equilibrium. Okay. So that is a very important result about potential games. So we are going to apply this particular result to our case of aggregative potential games. So the reason why the quasi potential function will be useful, now again, I mean, for a general potential game, except going to the Kuhn-Tucker problem of maximizing the potential function on X, there is no other way to characterize the maximizer, or there is no other obvious way. But it turns out that if you have an aggregative potential game, you can use the quasi potential function, which is a much simpler function because it is a one dimensional function. So finding the maximum of that is very easy, or at least much easier than finding that of the actual potential function, and you can just use the maximizer of the quasi potential function to identify the maximizer of the potential function and thereby identify the Nash equilibrium of the underlying game. Okay. So, that is the approach that we take. So, this is the general result on characterizing Nash equilibrium in aggregative potential games with negative externalities. That let F be an aggregative potential game with negative externalities. Okay. Suppose that a cost function is strictly convex. Recall that we had the earlier lemma which said that under these conditions G will be strictly concave with a unique maximizer. So, we denote that unique maximizer of G with alpha star, then the following holds. Okay. Suppose alpha star belongs to S. Now, alpha star is some number between 0 and m, and recall that our initial strategy set is an approximation of 0 and m. So, it is not necessary that alpha star actually belongs to S. Okay. So, if a strategy set is 0, 0.1, 0.2 and so on, and alpha star can be 0.15, then it will not belong to S. But suppose it does belong to S, then it turns out that the unique Nash equilibrium of F is just E alpha star. That is the monomorphic state E alpha star, or the vertex in the simplex in which everybody plays alpha star. Okay. If alpha star does not belong to S, okay, then also we can show that F has a unique Nash equilibrium, and in that Nash equilibrium only two strategies are possibly used. Now, forget about the notation and all that. Intuitively, what these strategies are that, so we have alpha star which does not belong to S. So, think of the value of strategy value which is just below alpha star and belongs to S, and just above alpha star that belongs to S. Okay. Then it turns out that in the unique Nash equilibrium there will be a unique Nash equilibrium, and that Nash equilibrium will be such that only these two strategies, at most these two strategies will be used. Okay. No other strategy can possibly be used. Okay. It is possible that only one of these strategies are used, but it is also possible that both are used. Okay. That means some people may use the strategy immediately above alpha star, and some people may use the strategy immediately below alpha star. Now, those details are not important. The important thing is that as you take n to infinity, as you make n larger and larger, the finite strategy set that we have will be an increasingly good approximation of 0m, the set 0m. Okay. So, therefore, these two values will also come arbitrarily close to alpha star. Okay. The one immediately above and the one immediately below. Right. So, therefore, for n large, this alpha star is a very good approximation of what the Nash equilibrium will be, and more importantly, because this is an aggregative game, it is a very good approximation of what the aggregate strategy level at the Nash equilibrium will be. If the Nash equilibrium is E alpha star, then obviously the aggregate value is also alpha star. But even if it is not alpha star, if the values are the Nash equilibrium strategies are very close to alpha star, okay, suppose the alpha star is 0.19, but 0.19 does not belong to the strategy set, then this is saying that in the Nash equilibrium 0.18 and 0.2 will be used in some distribution, but whatever distribution, the aggregate value of that will be close to 0.19. Okay. So, this is the idea that the aggregate strategy level in any Nash equilibrium will be either alpha star or close to it if n is large. Okay. Hence, the equilibrium strategy level can be characterized by the maximizer of the quasi potential function. Now, in the tragedy of the commons, recall that so it turns out, this is very easy to show. You can just show it using the quasi potential function, that alpha star will be characterized by the point alpha that equates the average product with the marginal cost. Okay, and hence in the tragedy of the commons, the equilibrium strategy level equates average product to marginal cost, which again is something that we probably already know from standard microeconomics, but this is another way to see that. Okay. So just an idea of the proof as to how we get this particular result. So since f is concave, we can use the earlier result by Sandom to show that to characterize Nash equilibrium, it is enough to characterize maximizers of f. Okay. So what we do is we then show that f has a unique maximizer if C is strictly convex. Okay. Now, this would have been trivial to show if f is strictly concave. I mean, if f is strictly concave, then obviously it will have a unique maximizer, but it turns out that f is not strictly concave. So therefore, it takes some work to show that f has a unique maximizer. Okay. So it turns out that for part 1 at least, part 2 is messy, so I am not going to get into that. For part 1 at least, the fact that this E alpha star is the Nash equilibrium comes from the fact that f E alpha star is equal to G alpha star by the definition of the quasi potential function. But recall that alpha star is the maximizer of G, hence it will be greater than any other alpha. I mean G alpha star will be greater than G of any other alpha. Okay, and this part follows from the strict convexity of S. Due to the strict convexity of S, this will hold. Okay, that means G alpha will be greater than f of x for any x such that Ax equal to alpha. Okay, now take any x, it will be equal to some alpha between 0 and m. I mean a of any x will be equal to alpha. So therefore, take any x, it will be, the aggregate value will be equal to some alpha between 0 and m. So therefore, G alpha will be greater than fx. Okay, but then G alpha star is greater than G alpha, and f E alpha star is greater than that, and hence E alpha star is the maximizer in the state space. Okay, so that's basically how we show that is the Nash equilibrium.
What are the additional properties for G? Is it?
No, G doesn't have any. No, G basically is just. I mean, the properties of G depends upon beta and C. So here we are assuming that beta is strictly decreasing and C is increasing and strictly convex.
Yeah, that's because of the nature of the externality that you want.
Well, yeah, the property of beta comes from the nature of the externality. C comes because that's a natural assumption. I mean, C should be increasing and maybe strictly convex also. I mean, that's a natural assumption to make. I mean, it would be a very weird cost function if it is declining. It can be linear. This will work with linear also, but I am not sure if it will work with concave C. Okay, so that's why I am assuming that C is strictly convex. Okay, so now anyway, so that's how we characterize Nash equilibrium. Now it turns out that now these are games in which we have externalities, either positive or negative. Well, at least in the particular example we are talking about here, the externalities are negative.
So the reason why I asked about the properties for G is, I mean, is it required to compare the so essentially it's like a single time, so Cournot solution kind of slicing of the optimization, right? So all the players are playing the same strategy. So what is the quasi potential gain?
No, not really. Actually, see, the reason why G is important here is that the intuition behind it is that in this sort of games, what is important is not x but Ax. Okay, so because only it's A of x that is the most important thing, and now A of x is just a one-dimensional variable between 0 and m. So therefore, we can reduce this function into a one-dimensional function. That's the idea. Okay, that is why we are able to get away by just looking at a simpler version of f, which is G, in which the domain is just one-dimensional.
So G is strictly concave on alpha.
Yeah, I mean, yeah, it will be, yeah, if under the assumption that beta is declining and C is strictly convex or linear also, it will be strictly concave. Yeah. No, no, it won't be a corner. I mean, yeah, it may be a corner solution, but not necessarily. Yeah. Okay, maybe I understand what you are saying. The maximizer of this may not be corner, 0 or m. Okay, but the equilibrium will be nearly corner. When you translate that maximizer into the state space X, the maximizer of that becomes either fully corner, which is E alpha star, or nearly corner. Yeah. So in fact, there is another version of this paper where I drop the assumption that the strategy space is finite. I fully work with the continuous case. In that case, equilibrium will always be corner. Okay, so now we all know that if there are externalities, then there will be inefficiency, in the sense that the equilibrium value will not be the socially optimal value. And indeed, if externalities are negative, then the equilibrium value will typically be higher than the optimal value. that is a standard again result from microeconomics. So, let us see whether we can capture that idea using this format. Okay. So, what we now do is we define an efficient state. X double star is efficient if it maximizes the aggregate payoff. Now, this is the definition of aggregate payoff, okay, for a general population game, that is, it is basically a weighted average of Fi weighted by Xi. Okay. Recall that Xi's are fractions between 0 and 1, these are probabilities. So again, due to the assumption that the mass is 1, you can think of it as aggregate payoff or as average payoff, they are equivalent in this case. Now, it turns out that if Fi has the is an aggregative game of the type we are talking about, then it takes this particular form. Okay, it's basically Ax times beta Ax minus summation of Cixi. So whatever x will maximize this particular object will be the efficient state. So it is maximizing the aggregate payoff in the population. So again, one can characterize it in a general case using again Kuhn-Tucker maximization, but it turns out that if we have the aggregative property, then we can construct a one dimensional analog of this function as this. So instead of looking at f bar x, we look at g bar alpha, which again is pretty similar to f bar. So instead of Ax beta Ax, we have alpha b alpha minus c alpha. So again, g bar is a function, is a one dimensional function. So again, I mean, there are some technical conditions and lemmas and all that. I am not going to for the interest of saving time, I am not going to go into all the details. But it turns out that we can show that this g bar has a unique maximizer, which we call alpha double star, okay, which will be typically less than alpha star. Recall that alpha star was the Nash equilibrium aggregate value. This alpha double star, which is the maximizer of g bar, will be less than that alpha star, and under the conditions of this lemma, f has a unique efficient state x double star that either equals or approximates E alpha star. Approximation and equal again depending upon whether alpha double star belongs to the strategy set or not. Okay. So therefore, the intuitively what we are saying is that at the Nash equilibrium, the aggregate strategy level is alpha star. At the efficient state, the aggregate strategy level is alpha double star, and due to this property that alpha double star is less than alpha star, we arrive at the conclusion that the equilibrium aggregate state, which is Ax star, which is approximately or exactly equal to alpha star, will be greater than the socially efficient aggregate state Ax double star. Okay. So again, to think about it, if you want to think about it in terms of the Cournot competition model, in the Cournot competition model, the efficient state from the limited perspective. So here, when we talk about a Cournot competition model, this is a partial equilibrium model in which the only population is the population of producers. We are not thinking about consumers right now. So from the point of view of producers, the efficient state is the one that will maximize their aggregate profit, which of course is the monopoly production level. The Nash equilibrium will be close to the competitive output level, because here the number of producers are close to infinity. Okay. And as we all know, the output at the competitive level is greater than the monopoly level. Okay. So that is basically what this result is saying. In the tragedy of the commons, it turns out that this g bar alpha, which is the one dimensional version of the aggregate payoff, can be written as pi alpha minus c alpha, pi being the production function, which can be written as this particular form. So alpha double star, which is the socially efficient aggregate state, will equate the marginal product to the marginal cost, which of course is standard. Okay. Whereas the Nash equilibrium, recall, would have equated the average product to the marginal cost, and due to the concavity of pi, we already know, but for the tragedy of the commons, we can directly arrive at this conclusion by recalling that pi is assumed to be concave. Okay. So therefore, we arrive at the result that in the tragedy of the commons, the socially efficient state or the socially efficient aggregate state is less than the Nash equilibrium aggregate state. That is, again, in terms of well-known story, the number of cows that actually ends up being grazed is more than the socially optimal number of cows that should be grazed on the field. Okay, so now let us talk a bit about the evolutionary implications of this result before we go into the one application of all this. Okay. Now I am not going to get into too much of technicalities about evolutionary game theory here because of lack of time, but it is well known that a variety of evolutionary dynamics converge to Nash equilibrium in potential games. Okay. So in our model we know that the Nash equilibrium is unique in our particular model that we have discussed. So these dynamics will converge. So if the equilibrium is unique, then of course these dynamics will converge to that unique equilibrium which is inefficient. Okay. So this is important because it shows that we don't really need strong. Now evolutionary game theory is based on very weak rationality requirements. So even if we weaken those rationality requirements, we still see global convergence to Nash equilibrium. Okay. And in this particular context of the tragedy of the commons, global convergence to the inefficient Nash equilibrium, socially inefficient Nash equilibrium, and therefore it explains therefore that even if we assume that people are less than fully rational, boundedly rational and so on, we will still experience problems like the tragedy of the commons. And if you believe that in reality people are indeed boundedly rational, then this is an explanation of why something like the tragedy of the commons is so common. Okay. Okay. So now so I am going to move to an extension of this paper, which is something that I have been working with on India here. So what I am going to do is I am going to apply this tragedy of the commons model to what we believe is a good explanation of why we see some particular pattern of growth and fluctuations in an economy. Okay. So what we will do is we will consider multiple rounds of evolution in a tragedy of the commons model. Now why should we think about the tragedy of the commons model to explain something like growth and fluctuations? Now if you look at economic history, you will find well known episodes like the Great Depression, the Great Recession and so on, where there is a period of rapid technological change, technological progress, okay, during which the GDP or the aggregate income in the economy increases by a lot, okay, but then it suddenly starts falling. Okay, the GDP suddenly starts to fall. Okay, now that triggers a thought that the knowledge that leads to technological progress at a macroeconomic level is actually a common resource. So think of the recent financial crisis or the dot-com boom and all that. The knowledge of IT, the knowledge of financial instruments and so on, anybody could have used it. I mean anyone with access to sufficient knowledge, I mean anyone can use it. Okay, so think of that stock of knowledge as the common resource that people can use. Okay, and now if you are thinking of the IT sector, think of the number of computers that you can use with that knowledge as the amount of investment or the amount of inputs that you can use. So think of the computers as cows and think of the knowledge as the common grazing field that people can use and take their cows to. Okay, so you can think of a situation intuitively where starting from a low number of cows or low number of computers, okay, people will start using the stock of knowledge, okay, and the stock of and when they do that, initially the payoff from that, the use of those computers, it will increase the aggregate payoff, the GDP. Okay, now it will keep on increasing till the number of computers hits the efficient level. Okay, but note that if indeed this is the case of the tragedy of the commons, that is the knowledge is the common resource, then the optimal number of computers is not the Nash equilibrium, just as the optimal number of cows is not the Nash equilibrium in the tragedy of the commons. People will not stop at the optimal number of computers. Okay, they will exceed the optimal number of computers and move to the Nash equilibrium, which is higher than the optimal level. Okay, so therefore the aggregate investment will start at a low level. Okay, it will increase to the optimal level, but it will not stop there. It will keep on increasing up to the Nash equilibrium level. Okay, now think of what will happen about to the aggregate income or the aggregate payoff. The definition of the optimal state is that it maximizes aggregate payoff. Okay, so from a point when the number of computers is 0 to the number of computers is efficient or optimal, the aggregate income will rise. Okay. But people will not stop there, they will continue to, even after that optimal point is reached, they will continue to increase the amount of investment. But during that phase, from the optimal level to the Nash equilibrium level, the aggregate income will start falling. It cannot rise, because by definition the optimal level was the maximum possible aggregate income level. So therefore, you can see this sort of pattern of fluctuation in this evolution of aggregate income. Starts at a low level, reaches the efficient level, which is the highest possible level, but it won't stop there because of the tragedy of the commons issue. It will start to fall. Okay, so that is.
I don't understand how are you relating to the tragedy of commons. What is the commons in our example?
Commons is the knowledge. Yeah, the knowledge doesn't have to be tangible. I mean, I think that the knowledge exists out there. Anyone, you, I, anyone, we can take our. Sorry.
Generally, tragedy of the commons, we say that
it is the common field.
Rivalrous.
It is the field or a lake.
In case of knowledge, it is not rivalrous. I mean, why you will not reduce imbalances you can. So I just don't understand how you are related to.
And the basic idea is more of effort investment. That you can have a certain technology, the initial and the basic intuition is something like exactly that of the tragedy of commons, that you come up with a new technology, you start investing on it, but you cannot, because there are multiple competing firms working on the same project, they will not stop at the optimum. Individually they will think that if the others stop and if I increase a little more of my resources, then that would be better. So the idea is that everyone will try to do that, they will overuse the resource and then aggregate payoff will go down. So now whether this is actually in a sense a good point, because we also received the call from the referee that whether leveling it knowledge is the best way to think about it or not. You can think about having financial derivatives, for example. If everyone is building on another financial derivative, then that becomes a problem.
See, the main issue here is not whether it will reduce the amount or not, but whether externalities are positive or negative. So if everybody is using the financial derivatives or increasing the amount of financial derivatives, does it have effect on others' payoffs or not? If the payoffs are negative, then probably this is a good model to think of. That's the idea. Yeah. So anyway, so what we do is to model this formally, what we do is we use the tragedy of the commons model with a productivity parameter which we call theta. Okay. So what we will do is later on we will introduce shocks to this theta. Okay. Now, so before getting into that, let's talk a bit about the type, what we mean by evolutionary game theory. Okay. So what we do is in evolutionary game theory is we introduce a dynamic. Dynamic is a differential equation system. Okay. So this, what this xi dot is telling us is how the value of xi is changing. Okay. Now this particular form, now there are number of evolutionary dynamics that are used in the literature. This is one particular form which we call the logit dynamic. Okay. Now it turns out that this is a very close approximation of the best response. Now what is the best response? That given the particular state x, okay, which particular strategy gives the highest payoff. Okay. Now using the pure concept of best response is difficult in evolutionary game theory, because best response may not be uniquely defined. I mean, there may be states where there is more than one best response. Okay. So to get around that problem, what we do is we look at an approximation of the best response, which is called a logit best response. Now the reason why this is an approximation is that now this is a pure probability distribution, in the sense that every strategy will receive positive. This is of course a probability distribution. Every strategy in this case will receive positive probability, but due to the presence of this eta factor, think of taking eta to 0. Eta is a positive number, but think of eta as something very close to 0. In that case, due to the exponential factor here, the best response will receive almost probability 1, not exactly 1, every strategy will receive some positive probability, but the best response will receive probability which is very close to 1. Or if there are 2 best responses, then both of them will receive probabilities very close to 0.5. Okay? But the point is that this is always uniquely defined, okay? And it is a very good approximation of the best response. So that's why instead of the best response, this is more commonly used. Okay? So the first term on the right hand side is what is called a logit best response. For eta small, it approximates the best response, and so on. And the rest point of the logit dynamic is called a logit equilibrium. You can think of the logit equilibrium as a very good approximation of the Nash. I mean, for all practical purposes, it is the Nash equilibrium. Okay? So what we then do is, so first let's take this example, okay, where we fixed theta to be 1, okay, or some value of theta. Recall that theta is the productivity parameter. We look at strategy set, which in this case we take a very simple strategy set, and then we assume some forms for a production function and a cost function. So this is exactly what is being shown here is what I tried to describe verbally. Okay, if you assume that this is the tragedy of the commons, okay, or this captures the flavor of the tragedy of the commons, then the evolution of the aggregate payoff takes this particular form. Okay, that is, it starts at a very low level, it rises to a maximum possible point, which is where the economy has reached the efficient state, okay, and then it starts to decline. Okay, so in a sense, you don't see a monotonic pattern of growth, okay, but a pattern where there is an initial increase in income and then a fall in the aggregate income. Okay. So what we then do is, again I'm being very brief here. What we then do is, so that was for a particular value of theta. Now if you want to talk about growth as well, we should have some way to introduce productivity shocks into the economy. So what we do is, we now introduce shocks to this theta. We assume that the evolution of theta takes this particular form. Okay? So the idea is this, that let's suppose that we have a given value of theta, the aggregate level of income has shown some pattern and has reached its equilibrium value. Okay? Then what we do is, we introduce, after that aggregate income value has settled down into the equilibrium given a particular value of theta, we introduce shocks to that theta. We introduce a shock to that theta. So here the shock is always positive, so it will, then theta will rise. Okay? When theta rises, then of course the game changes. The game is no longer a previous game, but it's a new game with a new equilibrium and a new efficient state. Okay? So then what we then do is, in the earlier theta, the economy had moved to one particular level. Okay? In the next round, the evolution will now start from that old equilibrium level to the new equilibrium level. Okay? And then we sort of track what pattern of fluctuation the aggregate income level displays. And it turns out that we get something like this, that if you introduce these repeated shocks to theta, then the aggregate payoff evolves in that particular way. So let's take any of this. So for example, let's say that we are at this stage, and then the economy has moved to the equilibrium value, okay, in which case then after a shock it moves up. Okay. Now here, this is what is interesting here, that it moves up, but then the increase is not monotonic, it then starts to decline, the intuition being that there is a tragedy of the commons here, okay, and it declines due to declines to an equilibrium level, okay, and so on. And we repeatedly see this pattern is being observed here. Okay. This is the evolution of aggregate payoff, this is the evolution of aggregate strategy. Okay. Now whereas the aggregate payoff has this increase and then the declining phase, okay, aggregate strategy is monotonically increasing, which again captures the flavor of the tragedy of the commons, that here is a case where the investment level in the economy is continuously increasing, but that is not being reflected in the evolution of payoffs. Payoffs increase sharply with every positive shock, but that increase is not sustained. Okay? It then declines to an equilibrium level and settles down at the equilibrium level till the next shock hits the economy. Okay? So that is that is basically the intuition. I mean, this paper is under revision, so we'll probably have to do some more work on this, but that's basically the basic intuition. Okay. So anyway, so that is the conclusion here, that we have defined aggregative potential games, we have considered games with negative externalities, we have characterized Nash equilibrium using the quasi potential function, and we have shown that such equilibrium is socially inefficient, due to which the evolutionary dynamics converge to the inefficient Nash equilibrium, and we have tried to apply these conclusions to an evolutionary model of growth and fluctuations. Okay. So anyway, so that's it.
Questions? Yeah, just give me 2 minutes.
Sir, in the last slide you showed that there are uniform shocks. These shocks may be of different variation.
Yeah, so again in the paper we also have a shock which is random. So then of course then also we still get the same pattern, but it's not so smooth, in the sense sometimes the jump is high, sometimes the jump is low, but this sort of pattern remains, that there is a jump and it goes up sharply, but that is not sustained, it comes down and settles down at a new level. So that probably doesn't depend upon whether this is constant or it is random.
I'm just trying to recap. So the idea that the equilibrium is more than the optimal.
Yeah.
How is that coming? Because of costs.
No, that is coming. The main reason that is coming is because of the fact that this beta is declining. So that is there, or in other words, that externalities are negative.
Okay, negative.
Yeah.
So this can be applied to, I'm just thinking, for example, urbanization, over-urbanization.
Yeah, that is the tragedy of the commons. Yeah, any use of natural resource is probably
For example, I mean, I don't know how this would relate, but there's this thing of optimal urbanization.
Okay.
In any region. I mean, there's this whole theory of urbanization, and there is classic economies and diseconomies of agglomeration.
Yeah.
So could this be applied to that framework in terms of saying economies agglomerate, and then there's an they pass this threshold, and because I don't know how I would relate that to tragedy of commons. But I'm just
No, yeah, so this is tragedy of the commons because since the city is commonly accessible.
okay. But then the cost.
We have a quick take this tragedy. That would be a tragedy of commons, as they pointed out, because that there can be if more than optimal number of people can come in, and the amenities may go down and so on. The problem of repeated application of tragedy of commons in that sense is that we do not really see one city growing, flourishing, then destroying, and then again it's creating. So business cycles are basically something of that sort. That you have a sequence of activities coming up, it increases, people start investing, then they think that it was something horrible decision. So the bubble pops. But then you have another new technology coming up in some relative. So basically we are trying to capture that idea. With cities, a one-time tragedy of commons will work. Having it repeatedly, I can't think of an example where
Surat.
Yeah, unless you can think of a city where it's repeatedly invaded and destroyed, and again it gets overcrowded, and again it is invaded and destroyed.
Surat is a classic example. Okay, no, I think it's very interesting. Very interesting framework.
So in Surat, what population fluctuates a lot?
Surat, I mean, on a last 600 years time scale,
it has been destroyed and
it's actually fallen by half, and then again, even Delhi.
We should steal those data.
But
that would be an interesting application for our expert.
Yeah, if you want to write something about that, we can certainly explore it. Yeah.
Even in the US, I mean, again, because I do urban economics, I'm from that perspective.
Yeah.
But in the US, you have cities which decline actually over time. But I don't know how many of them have been mounted back as well. But yeah, I mean, I agree. With growth, it's a much more appealing connection to make.
So since I don't know this literature, so this is building on some.
So the earlier part of the paper, pure theory, that is my own work, is already published.
Okay.
So the later part of Roland publication is something it's ongoing learning.
So this aggregative games is attributed to whom?
But there is a work paper by someone called Cournot, or I don't know, some French pronunciation, Cournot. It's just published in Mathematical Social Science. Cournot. Yeah, from it is. I don't know, maybe I think.
Yeah, second part.
Yeah.
So evolutionary thinking appears to be quite a common goal. Not very common, but these are certain subsets. Alright, so let's present. If any other questions, you will be there in the campus till Saturday.